Alright, so let's talk about some random variables. So, topic 11, random variables. We're going to talk about what a random variable is, determine how to find a probability distribution, determine how to find the expected value, determine how to find the variance and standard deviation, determine how transformations of points change the expected value and the standard deviation. So, a random variable is a variable that expresses the change in a random phenomena. Do 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 do. It's not really that word in that song, but you know, it still sounds pretty convincing. But yeah, so it's a variable that expresses the changes in a random phenomena. So things that are random can be changed into variables. I know, it's like algebra and statistics. It's like all your worst fears in one place. Example, suppose you have 5 quarters. We can create a random variable x which refers to the number of heads that can be flipped in 5 quarters. So x equals 1 means that you are flipping 1 head in 5 quarters. So what we're going to do is we're going to create what's called a probability distribution. So essentially, it's all the possibilities in a particular variable set. So, for instance, we just said x equals 1 means you're flipping 1 head in 5 quarters. What we're going to do is we're going to create this probability distribution to be a list of all the different probabilities that can occur from the outcomes of the random variable. A probability distribution is valid if all the probabilities equal to 1. And what that means is if I add all of these probabilities together, because it's kind of a slightly misnomer there, that should equal 1, because it's a sample space again. And remember, sample spaces have to add up to 100%, so a probability distribution has to add up also to 100%. So this whole thing has to be 1. So let's look at how to create a probability distribution in this situation. So we have 5 quarters again. Well, I think last time we had 3. But we're going to talk about 5 quarters this time. So for 5 quarters, first off, let's talk about how many possibilities that is. So 5 quarters means, remember we have the general counting principle, we have 2 for each possible quarter, so it's 2 to the 5th power, which gives me 32. So there's 32 different possibilities. Now to create our distribution, we're going to have x equals x, and we're going to have the probability of x equals x. And so over here, we can have, because we're going to base this off of heads, we can have no heads, we can have 1 head, we can have 2 heads, we can have 3 heads, we can have 4 heads, and we can have 5 heads, all 5 heads. You can't have anything else. You can't have -1 heads. You can't have 6 heads, so there's only 5 coins. Okay, and all these probabilities will be out of 32. So what's the probability of having no heads? Well, that would be having no tails. And you're gonna, all tails rather. And you're gonna do that one way. So the probability of having no heads is 1 out of 32, since you're gonna have all tails. Incidentally, what's the probability of having 5 heads? Well, that would be the probability of having all heads. So that would also be 1 out of 32. So this one's actually kind of very symmetric. What's the probability of having 1 head? Well, I can have heads, tails, 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 and I can float that head into any position, and there's 5 positions. So I know that my probability of having 1 head is 5 out of 32. Same thing for here. If I had 4 heads, I can float that tail into any one of 5 positions. So I have 5 out of 32. Okay. Then, what about 2 and 3? Well, I could sit here and try to figure it out. And there's a way to do it with binomial probability, but we haven't gotten to that yet. So what we're going to do is this. I have 1, 5, 5, and 1 possibilities. So that's 12 altogether. I get that from adding 1 plus 5 plus 5 plus 1. Okay? So that's 12 altogether. So I have 32 altogether with my coins. So I'm going to take that 12 and I'm going to deduct it from 32 to get 20. And then since it has to be an equal amount, I'm going to then divide this by 2. That gives me 10. I get 10 out of 32 and 10 out of 32. And so this is my probability distribution. So I probably could, I'll write this a little bit bigger down here so you can see the probabilities a little bit better. So x equals 0 is 1 over 32. X equals 1 is 5 over 32. X equals 2 is 10 over 32. X equals 3 is 10 over 32. X equals 4 is 5 over 32. And then x equals 5 is 1 over 32. And that's it. That's a probability distribution. It's not too bad. Let's find a probability distribution of the dice. So let's find the probability distribution of the dice. Well, same thing as before. I think I can fit it all in here. You get x equals x, probability of x equals x. So remember when it comes to dice rolls that everything has to be out of 36 because it's 6 times 6. So we get x equals 2. And how many ways can you roll a 2? Well, 1, a 1 and a 1, so we get 1 out of 36. Now you're going to see a pattern start to emerge here. How many ways can we roll a 3? Well, 1 and 2 and 2 and 1, so that's 2 out of 36. And yep, ultimately it's going to climb 3 out of 36, 4 out of 36, 5 out of 36, and we get 6 out of 36. And that's where it stops, and this one has the most, and that's why 7 is lucky, if you didn't know. Because it has the highest probability of being rolled. And it goes down to 5 out of 36, 4 out of 36, 3 out of 36, 2 out of 36, and then 1 out of 36. So that is your probability distribution. If you add them all up, it becomes 36 out of 36, so that's 100%. Okay. So now, an expected value. An expected value is another name for a mean. Basically, you're finding the mean of a random variable. You find this by taking every x value and multiplying it by its probability and adding all the products. So we'll start by finding the expected value of the coins. And so when you look at the symbolism for expected value is e of x. So if you take for a second the quarters, I can rewrite my probability distribution right here. So we got x equals 0, which was 1 out of 32. We got x equals 1, which was 5 out of 32. X equals 2, which is 10 out of 32. X equals 3, which was 10 out of 32. X equals 4, which was 5 out of 32. And then x equals 5, which was 1 out of 32. Okay, we can do that. And so then to find the expected value, what I'm going to do is I'm going to take every outcome and I'm going to multiply it by its probability. So 1 times 5 over 32, 2 times 10 over 32, plus 3 times 10 out of 32, plus 4 times 5 over 32, plus 5 times 1 over 32. Okay, so let's see. That's just going to zero out, so there's not even really a reason to write that again. But 1 times 5 out of 32 is 5 out of 32. 2 times 10 is 20, so 20 out of 32. 3 times 10 is 30. 4 times 5 is 20. 5 times 1 is 32. So 5 times 20, 5 plus 20 plus 30 plus 20 plus 5 gives me 80 out of 32, which is 2.5. Okay, so what that means is this. You should expect to get 2.5 heads every time you flip. Or on average, rather. On average, you should expect to get 2.5 heads. Which, when you think about it, doesn't make sense, because how do you get 2.5 heads? That's just statistics sometimes. If you are as old as me, and it dates me a little bit, when they were running ads when I was a kid, they used to say, every household had 2.5 kids, and people would be like, what does that mean? How can you have 0.5 of a kid? It's just how statistics are worked out sometimes. I don't know why they don't change it, but you think of it as like this: you should on average get somewhere between 2 and 3 heads on average. So let's look at the dice, and the dice will probably be a lot more what you think it should be. So I'm going to assume that you are looking at the dice right now. So you would do 2 times 1 over 36 plus 3 times 2 over 36 plus 4 times 3 out of 36 plus 5 times 4 over 36 plus 6 times 5 over 36 plus 7 times 6 over 36 plus 8 times 5 over 36 plus 9 times 4 over 36 plus 10 times 3 over 36 plus 11 times 2 over 36 plus 12 times 1 over 36, which gives me, let's go down here, 2 over 36, 6 over 36, 12 over 36, 20 over 36, 30 over 36, 42 over 36, 40 over 36, 36 over 36, 30 over 36, 22 over 36, and 12 over 36. And you definitely don't want to simplify them, because when we add them up, they all have to be over the same denominator. And what it should give me is, let's see if I add all these up real fast, it should be 252 over 36, which gives me 7, which is pretty much what you would think, basically. On average, you should be getting a 7. Makes sense. Again, that's why 7 is lucky. Okay, so let's look at some other problems that involve expected value. The way that the SAT used to work is that if you got a question right on the SAT, you get a point for that question. If you got the question wrong, you would lose a quarter of a point. If you chose not to answer, you didn't lose a point or gain a point, so that's really negligible. Each question has 5 possible answers. What is the expected number of points if you choose to guess on the old SAT? Well, you only have 2 basic outcomes. You can gain a point, or you can lose a quarter of a point. And since we have 5 answer choices, the probability of getting something right if I guess is 1 out of 5. And the probability of not getting something correct is 4 out of 5. So I'm going to have 1 times 1 out of 5 plus negative 1/4 times 4 out of 5. So what happens is this becomes 1 out of 5, and this, well, I can cancel that out, and I get negative 1/5. So my expected value is 0, which is why we used to tell people not to guess. Because in the long and short of it, you're not really gaining any points if you guess. Of course, it's different now, because apparently you can guess, and you might luck out into a point, which I think makes the SAT a lot more pointless than it used to be. But you know, who am I to say? Okay. So you decide to put $1,000 towards a new stock. Stockbroker predicts that there is a 15% chance that the stock could explode and you could make $10,000. There's also a 55% chance that that you will lose all your money. There's also a chance that you will break even. What are the expected earnings of this stock? So, we're talking about earnings here. So when we look at it, we got three possibilities. So there's a 15% chance that the stock could explode and you could make $10,000. But you're not really making $10,000 because you invested $1,000. So in reality, you're making $9,000. There's also a 55% chance that you're going to lose all your money, which means you're going to lose your initial investment of $1,000. You could also break even by gaining nothing. And so let's see, the probability of gaining nothing would be 0.15 plus 0.55 is 0.70. So if we subtract that from 1, it gives me 0.30 or 0.3. And now I have 100%. And so my expected earnings are 9,000 times 0.15 plus negative 1,000 times 0.55. And really this last one's negligible. Again, it's just going to be 0. So if I do the quick math on this, I'm going to get 1,350 here minus 550. And that's going to give me $800. So on average, I should expect to earn $800. Okay. In a game of chance, a player pays $5 to pick a marble out of a jar of 5,000 marbles. If they pick the one gold marble, they win $10,000. If they pick one of the 2 silver marbles, they win $1,000. If they pick one of the 3 green marbles, they receive $500. If they pick one of the 5 blue marbles, they receive $200. If they pick one of the 10 purple marbles, they win $10. They pick one of the 12 yellow marbles, they win $2. And if they pick one of the black marbles, they win nothing. So, what is the expected earnings in this? Well, we need to look at every single one of these individually. Remember that you got to deduct your 5 at first. So, because we're paying $5 to get in, so we're really not winning $10,000. We're winning $9,905. Then you're really not winning 1,000. You're winning 995. You're not winning 500. You're winning 495. You're not winning 200. You're winning 195. You're not winning 10. You're winning 5 because you're deducting 5 every single time. And you're not winning 2. You're winning negative 3. And then the last possibility is that you lose your money. So now the probability of winning 9,995 is 1 out of 5,000 because you got that one gold one. 2 out of 5,000 here. 3 out of 5,000. Where am I at here? 5 out of 5,000. 10 out of 5,000. And then 12 out of 5,000. And then so to figure out what's left, all I gotta do is add the numerators together. So that gives me 33 and deduct it from 5,000. And that gives me 4,967. That way it adds up to 100, or adds in this case, the numerators add up to 5,000, and we get 100%. And so now, to find my expected earnings, I'm going to take 9,995 times 1 over 5,000 plus 995 times 2 over 5,000 plus 495 times 3 over 5,000 plus 195 over 5 over 5,000. Where are we at? Plus 5 times 10 over 5,000. Minus 3 times 12 over 5,000. And then minus 5 times 4,967 over 5,000. Okay. And then, so that'll give me, let's see, 9,995 over 5,000 plus 1,990 over 5,000 plus 1,485 over 5,000 plus 975 over 5,000 plus 50 over 5,000 minus 36 over 5,000, and then 24,835 over 5,000. And if I just go ahead and add and subtract the numbers on top, I get, just make sure I'm okay here. Yep, that comes out right. Okay, so I'm going to get negative 1,376 over 5,000, which ultimately gives me negative 208. So negative $2.08, which means on average you stand to lose on this game, which is most gambling games anyway. So yeah, you should know that in most gambling games you always stand to lose. It's how the casino wins. Okay, so then we have variance and standard deviation. It's pretty much the exact same things you did last time. For variance and standard deviation, it's just as bad. So here are the steps. You're going to find the expected value, which can stand in for the average again. Subtract the expected value from the data points. Square the results, multiply by the probabilities, add all results, and then square root. So the things that are different is that you don't actually divide by n minus 1, but you do have to multiply by all the probabilities. So let's take a look at that in action. We'll take a look at the quarters again. So if you recall, we had 0, 1, 2, 3, 4, and 5. 1 out of 32, 5 out of 32, 10 out of 32, 10 out of 32, 5 out of 32, 1 out of 32. And remember that the expected value was 2.5. So what's going to happen is this. We're going to do 0 minus 2.5, 1 minus 2.5, 2 minus 2.5, 3 minus 2.5, 4 minus 2.5, and 5 minus 2.5. So it's going to be negative 2.5, negative 1.5, negative 0.5, 0.5, 1.5, and 2.5. Then I'm going to square. So let's see. This would be 6.25. Pretty sure that's 1.25, but let me just double check real fast. Oh, 2.25. I'm glad I checked. Yeah, 15 squared is 225. I don't know why I had that issue. So then, that's a good thing about this being symmetric. The numbers, I don't have to do half the work. And then I'm going to multiply it by 1 over 32, 5 over 32, 10 over 32, 10 over 32, 5 over 32, 1 over 32. So I do the math on that. Okay. And when I add everything up, I'm fairly certain I get 1.25. And for all my students who are watching this, it's because I didn't round this time that I'm actually going to get 1.25. Yep. Okay. So that would be my variance. And then my standard deviation. So I'm going to square root 1.25. And I get 1.1180. Now, we can do this all in StatCrunch. So let me pull that up real fast. So if I pull up StatCrunch, okay. Let's bring that right in. Oops, I brought the wrong one in. Let's bring that one in. Okay. So now what I have to do is this, and I'm just going to label this one outcome. I'm going to label it probability. So my outcomes for the coins were these. And what I need to do is I need to change my fractions into decimals, unfortunately, because this won't work unless it's all in decimals. So let's get the correct decimals, shall we? I get ready to put my calculator back on charge. Okay. So then, in order to do this in StatCrunch, all I have to do is go to Stat, Calculators, and then go down to Custom. And then what I'm going to do is put my values in, and that's where my outcomes go, and my weights go with my probabilities, and hit Compute. And it'll give me my expected value, which is my mean, and my standard deviation. And you could do some fun things on it if you want. I'm personally not worried about that right now, so let's minimize that. And that's how you would do your standard, find your expected value and standard deviation on StatCrunch. Okay, so let's go back here real fast Just view one more thing. So we got the love game. On Valentine's Day, a certain restaurant does promotion where at the end of your meal you pick from 1 of 10 card numbers, 0 through 9. If you pick the number 1, you get $20 off your meal. If you pick any odd number, except 1, you get $4 off your meal. If you pick any even number, you get $0 off your meal. So, I'm going to create a probability distribution. So we got 3 possibilities. Either you get $20 off, you get $4 off, or you get $0 off. Probability of getting $20 off is 1 out of 10. The probability of getting $4 off would be 4 out of 10 because there's 5 odd numbers, but you deduct the one from it, and then the rest is just 5 out of 10, all the even numbers. So that's your probability distribution. Your expected value, I'm not really going to go ahead and put this into StatCrunch just because this one's pretty easy. I'm just going to do 20 times 1 over 10 plus 4 times 4 over 10 plus 0 times 5 over 10. So that gives me 20 over 10 plus 16 over 10, which is 36 over 10, which is $3.60, because we're talking about money. So on average, you should expect to get $3.60. And then if I wanted to do the variance in the standard deviation, so I got 20 minus 3.6, 4 minus 3.6, and 0 minus 3.6. So 16.4, 0.4, and negative 3.6 square. So I'm going to run out of room. Oh boy, so let's go down here with everything and say 268.96, 0.16, and then 12.96. And I gotta multiply by the probabilities. So should give me those numbers, and then if I add all this together, I get 33.44, which is the variance. And then the standard deviation, I'm just going to square root it. So 5.7827. Okay. Alright, so now we got to keep those numbers in mind because there is something that's going to happen. So what's going to happen is this. Suppose the same restaurant decides the hour of love is 8 p.m. for some reason and decides to add $4 to all the discounted prices. So what's going to happen is the probabilities don't change, but your ultimate prize goes up to 24. Your secondary prize goes up to 8. And you get $4 in the last one, so you're guaranteed to go get a discount in some way. So the question becomes, what happens now? And I don't physically want to find the expected value, again if I don't have to, because I know the expected value from the last one was $3.60. If I don't have to do anything, if I can do something to this to manipulate this, I would love to and not have to do all that work, and it turns out I can. So as long as they're all being added the same thing, I can just take that thing, which in this case is 4, and just add it right to it. So $3.60 becomes $7.60. So that's my new expected value. Now what happens to the variance and the standard deviation? Well, they're still the same. So I'm just going to rewrite the standard deviation down here, which was 5.7827. Now, the reason why they're still the same is because standard deviation and variance represent a distance. And the distance between the points has not changed. It's still the same length away. Therefore, the distance doesn't change, the standard deviation doesn't change. Remember, standard deviation is an average distance back to the mean. So that's why that doesn't change. And there's just those rules for you again. The expected value increases or decreases by that amount, and the variance and standard deviation stay exactly the same. Okay, so suppose that if you enter the restaurant alone on Valentine's Day, the restaurant takes pity on you and doubles your discount. Now this is different. This is going back to the original, so not the 24, but this is going back to the original, which was 20, 4, and 0. So under this scenario, when you get doubled, we're going to end up with, I don't know why I put X there, but in this case it's 40 if you doubled 20. It'll be 8 because you doubled 4, and then still 0 because when you double 0, it's 0. Probabilities haven't changed. So again, I don't really want to have to rework the whole expected value, but if we were to, what would it come out to be? Well, it turns out the rules for expected value just continue. If I'm going to double all these numbers, I'm going to double the expected value, and doubling the expected value gives me 7.2. And then for my standard deviation, well, it is changing this time, but luckily it's going to follow suit. And I'm going to just multiply that by 2. And so that's going to give me 11.5654. So my expected value and my standard deviation are both going to double when I double all the numbers. Now the variance is a little bit different. It's going to, since the variance is the square, so the variance of x is the standard deviation squared. Since we square root the variance to get the standard deviation, the variance has to be the standard deviation squared. You would take the variance and multiply it by 4. Or what most of my students do to make it easier, they just take this number and then just square it to get the variance. So that's probably an easier route to go. But here's the rules. The expected value is going to be multiplied by whatever that thing is, it's multiplied. So if it's 2, you're going to multiply by 2. If it's 3, you're going to multiply by 3. If it's 4, you're going to multiply by 4. Standard deviation is also multiplied by the exact same thing. And that's it.